So I recently came across this problem and I thought it was pretty interesting. So I wanted to create a video that kind of went through the solution of this problem. And basically, the main idea of this problem is that you're given an array called P, and you want to connect all of these indexes in the array, kind of like a graph where a connected component in a graph where you can reach all other indexes through a series of edges. So for example, I would create a edge between 2 and 6, 4 and 7, 6 and 14, and then 21 and 7, and 21 and 14. And from here, let's say I started at index 3 and I wanted to reach index 2. I could take the series of edges from 7 to 21, 21 to 14, 14 to 6, and then 6 to 2. And the way you create edges in this problem is that you have to find is that it costs you a price of the greatest common divisor of all the values in between those two indexes. So for example, if I wanted to create an edge between 4 and 7, I would have to find the greatest common divisor of everything here. So that would be 4, 6, and 7, and that would be equal to 1. And the main idea of this problem is that I want to make this entire array into a connected component so that while also making the price of this of making this connected component as small as possible. So in this problem, the answer would be 5 because, uh, for example, I could create an edge between 4 and 21. I would create an edge between 6 and 21, and then an edge between 2 and 7, and an edge between 14 and 2, and then an edge between 21 and 2. And the GCD of this would be equal to 1, and the GCD of this would be equal to 1. Also, this would be equal to 1. This is equal to 2, actually. And wait, hold on. No, the GCD of this would actually equal to 1, and then the GCD of this would be equal to 1 too. And the sum of all of these prices would be equal to 5. So the first thing I noticed about this problem is that mathematically, let's say I had the greatest common divisor of 4 and 6, and that would be equal to 2. But say I wanted to add a new value like 7, then my GCD would be equal to 1. Or if I wanted to add 2, I could do GCD 2, 4, and 6 is equal to 1, equal to 2, sorry. And the main idea from this is kind of that if you add a new value to a greatest common divisor equation, the new solution or new result will never be greater than the original result. So you can kind of use this to logic out the idea that you want your edges to be as far away from each other as possible to minimize the cost. So let's say I wanted to make an edge between maybe 7 and 14, right? Obviously, if I made an edge between 7 and 14, that cost would be equal to 7. But let's say what equal to 7. But what if instead I made an edge between 7 and 2, and then I made an edge between 14 and 2? It might seem like not good at first, but once you do the calculations, which is GCD of 2, 4, 6, 7 is equal to 1, and GCD of 2, 4, 6, 7, and 14 is also equal to 1, you realize that the cost of this is 2, which is much smaller than the original cost, which is 7. So from here, we can realize that since we want the edges that we make to be as long as possible, we can choose to either create an edge between the current value and the first value, or the current value and the last value. And we do this, and to pick between the two, we just pick the value with the smaller greatest common divisor. And we do this because we want, as I established earlier, we want to have the cost to be as small as possible. And for the cost to be as small as possible, we want the distances to be as long as possible. And for them to be as long as possible, we can pick the first value or the last value. And another thing we notice is that we can kind of think of this graph as a tree. And this is because each value in between the first and last value only has to connect to one of them, because at the end we can connect the first and last value together, which completes the tree. So for example, I start from this middle value, which is 4, and the GCD between 2 and 4 is equal to 2, and the GCD between 4, 6, 7, 14, 21 is equal to 1. So I obviously would want to pick the edge that connects to 21 because it gives a smaller cost. And the same thing would be for 6, and the same thing, and for 7, I would want to connect to 2 because the GCD is smaller, and for 14, I would want to do the same. And now we see that some values are connected to 2 while some values are connected to 21. And the graph isn't fully complete yet because those two chunks aren't connected to each other, because visualize 21 is connected to 4, and 21 is connected to 6, and 2 is connected to 7, and 2 is connected to 14. And they can't, if I was at 4, I can't reach 7, so I want to find a way to connect these two. And the easiest way I can do this is by connecting the first value and the last value. And this is beneficial because, uh, as I stated earlier, that when creating edges, I want the distance to be as long as possible. And since this is the longest distance possible in this array, my greatest common divisor will be as small, will be basically the smallest possible greatest common divisor that I can achieve with these array. So the steps to solving this question is that we want to, for each value between the first and last value, we choose between connecting with the first value or the last value, and at the end we connect the first and the last value. So now we can look through some of the code I wrote. So first I insert all of the values that were given, and then from there I create a prefix and suffix greatest common divisor. And what each of those do is the prefix, it looks at the first x or I amount of values and finds the GCD. So this prefix right here, it would find the GCD from 2, and then the GCD 2 to 4, 2 to 4 to 6, 2, 4, 6, 7, 2, 4, 6, 7, 14, and so on. And this is beneficial because it takes O of n time to calculate the GCD, and it only does it once. But if I were to just do this manually, say I wanted to find the GCD of 2, 4, 6, 7, 14 each time, then it would take me O of n squared time. And I kind of do the same with the suffix, but I do it backwards. So I first find the GCD from 21, and then 21 to 14, and then 21, 14 to 7. And then after that, I want to calculate the answer. And as I said before, for each value in between the front and then the start, between the front and the start, I add the minimum GCD between all the values from the start and the current value to the end. So that is seen here. And then I set the answer initially to the suffix of 0, because that will be the GCD of the entire array. And that's how I link the two connected components together. And I print out the answer, and then I can try submitting this right now. If I, okay, yeah. Oh, I submitted the same code before, but uh, yeah, the submission's right here, and I will put the code in the description. Thank you for listening.